Okay. All right, everybody. Welcome to HAL's August 2026 meeting. And let's go to the presentation. Here we go. So our agenda this evening is pretty standard stuff. We have a great speaker. Ernie Wright is with us here this evening, and you may remember it back in February. He did a brief talk to us about the Artemis mission, and there was a lot of engagement. So we're very happy that Ernie was able to put together something for us for this evening. I'm looking forward to that presentation. So the first thing we like to do is to just check to see if we have any new members in the room or online. Anybody new to the club here this evening?
I'm thinking about being a new member.
You're thinking about it. What do we have to do to push you over the edge?
I think it's occurring. We'll see.
Welcome. We're glad you're here with us, whether you are a card-carrying member or not. That's great.
We're thinking about applauding.
Anybody online? No, okay. We have a C-Star program, and basically it is a C-Star S50, which we've had for about 3 years, and the club lends it out. So if you are a club member, you can borrow it for a month and take pictures like what SunGuard did here. This is N13. You want to tell us a little bit, or did he come up for a second? Tell us a little bit about your experience this past month and what you did with it. Up here, just nice and loud.
Okay. Well, this is a really wonderful program. This is the second time I'm borrowing it from HAL, and you don't have to. I mean, I know most of you are experts here in astronomy. I was not. I started doing this only a couple of years back after joining HAL. I found it pretty simple and easy to use. And not only that, the club was gracious enough to buy accessories to the C-Star telescope. They have got a very nice tripod. That's really, and a tripod with adjustments for leveling.
Right.
Which is, yeah, it's very critical, because without leveling, it will not start focusing, and that's a very good accessory. And then they also have solar filters, a couple of one I bought new because I thought I damaged the previous one first time around, but looks like the previous one was also good. So there are 2 solar filters. So if you are planning to borrow this from the club, it's a wonderful, very good idea. And you don't need to know anything. It just does it for you. You just set it, go, and then it starts capturing it. The only thing I don't know is, maybe I could have just done some research, is sometimes it doesn't stack. For example, when I was imaging the sun, it did not stack. I don't know why.
Because stack with the sun. I'm not sure. Anyone, Wes, you have any idea, Phil?
Yeah, so the sun is difficult because one, it's the pixels are always moving, because the atmosphere, you see it moving more with the sun because of size and heat and everything else like that. So if it's not, if there's atmospheric movement at night too, it'll skip that frame. But the sun, it's always changing because it's so close, like 8.5 light minutes away. So you really can't stack the sun.
I can't stack.
Yeah,
It doesn't stack.
It's not that they won't do it, it's just pixels are moving all the time and there's no 2 the same.
But can you force it to stack?
No.
You can't.
You could do it yourself in external software.
Oh, so you have to do it post-processing.
Right.
Yeah.
Okay.
I also wonder if it's programmed just not to stack if if you tell it it's pointed at the sun.
Yeah, I think it's probably a lot how my Celestron origin works. So for very bright objects, it takes snapshots, because if you stack the images, it just comes out as just a blur of bright light.
Right. Because of the brightness.
Yeah.
Yeah, but the moon came up very fine. I mean, the moon imaging was nice. And what I was surprised was, Tom, you could use it in your backyard. You don't have to go hunt for a night sky or a dark sky area. And although I went to a dark sky park and then imaged it, this was imaged, I think,
I've got some more of yours.
if it is, yeah, the dark sky area. Dark sky would help it. I mean, you would get a very good image, but even without that, even in your own, it's a bottle 6 or 7, I think, my backyard, in my deck. And there are a lot of lights around. Everyone has got a motion sensor light and stuff like that. So even with that, it took very nice images.
Awesome.
So it was a nice program.
Well, I'm glad that you've made use of it and you've done great with it, and you're going to be our C-Star expert. So when somebody has a problem, you know what? Call up somewhere and ask him about it. But no, seriously, I'm so glad that you had an opportunity and you made very good use of it this
Yeah.
month.
And
So since the individual who's going to take it this evening is sick, if there's been a lot of flu going around or whatever, if you want to take it for one more month, feel free.
yeah, and I would also, can someone here take it in case they want to?
Is anyone here already registered on the sign-up sheet? I don't think so.
That's okay.
Yeah, you kind of have to be on the sign.
On the list. Okay, so next month, is it possible for me to not show up at this meeting because I would be out of the country
We'll make
around that time?
arrangements. We'll make arrangements for you.
All right, but it's a very good program. You should be on you should get on the list, the waiting list, and it's online. If you go to HAL's website, you have a tab for that, and if you get on the list, you will be the next.
Awesome.
But there are a lot of people who sign up a lot very fast, so you got to
It
be.
can take a second turn. It's just that we do prioritize people who have not had an opportunity with it yet.
Yeah, but all in all, I want to thank the club.
Okay.
Without the club's the loaner program, I would not be using this. Thank you.
Awesome.
How many C-Stars are in rotation right now?
Just one.
Oh, just one. And do we have a sense for how long the waiting list is right now?
I think there are 3 people on the list who have not had a turn yet.
Oh, okay.
Dave, are you online? I know he was going on vacation and he didn't think he would be checked into the room yet. So we're just going to table this one till next month and he'll talk to us about the book of the month for September. So the weather has not been the greatest, but we have had some impromptu star parties out at Alpha Ridge. July the 13th, Wayne hosted one. He said the conditions were cool, calm, but still a little smoky. The light meter is reading 19.88, which I think is pretty respectable.
It's pretty respectable. A really good night will be right at 20 or a little fainter than 20.
So we had 7 members attend, and you can see a variety of targets were being imaged, a variety of equipment. And on July the 23rd, Ernie Morse held one. Again, conditions were pretty good with above average skies. I do remember that night I was doing a little bit in my backyard. It was a fairly good night. There were 13 members for that one. A lot of imaging activity, a lot of different targets, lots of equipment. And there were 2 new members who also were able to come and use their StarSense Explorer. So the bottom line is, again, as a HAL member, one of the benefits that you get is that members will call an impromptu star party. You have to be on the email list to get the announcement, but you can go out to the site and bring your telescope, your binoculars, whatever, and enjoy an evening in slightly darker skies. So up next, we have a member star party this Saturday, and then we will have our public star party the following week on the 22nd. We had another great event, August the 8th, just I think last Saturday. We had the mentoring event. Basically, Jose and Wes went out to Alpha Ridge and people came out. 18 folks came out with a variety of equipment that they wanted some coaching on or some help on. There was a lot of hands-on help. There were some new owners of a 16-inch Dobsonian, and they finally were able to experience first light, even though it wasn't a great clear night. They were able to get things together and look at some of the brighter stars. Somebody with a Meade 90 EXT got it aligned for the first time. There was some help and coaching on how to use binoculars with the spotter scope. I think you guys also did a tour of the halo inside.
Jose did that, yep.
Awesome. Gave people an idea of what that's all about. In terms of observing, Arcturus and Vega were out and were used for 2-star alignment to show people how to do that. And the bottom line is that you had many first-time visitors, and there was a strong emphasis on learning and welcoming new members. I think this is one of the best things that the club does in terms of trying to help folks. If you have a new telescope or you just need some coaching, try to do this at least once or twice a year. So you should be on the HAL email list so that you can be aware of when these events are happening.
Jim, quick question. Is the background on this picture, is it real or?
See the little co-pilot signal?
It's too good to be real.
It's too good to be true. Too good to be true. Okay, we're gonna have a HAL yard sale.
Oh, wow.
And we're cleaning out that storage shed, so it's your chance to pick up some equipment at bargain basement prices. It's going to be, we're targeting, hopefully, the members' start party. Again, another reason to be a member of HAL, because member start parties are for members only. And that's Labor Day weekend. So that Saturday, September the 5th, is when we're targeting to have this event. It'll be out at Apple Ridge. It'll be set up outside the halo. We've got mounts, 8 and 10-inch Dobsonian, a Meade ETX, a refractor. There's a lot of stuff. Probably in early September, we will publish the list so that you can kind of see what all we're going to have. And we are working on, there's somebody else that may be donating some very nice pieces of equipment. If we can pull that off before the deadline, those will also be in the yard sale. So important, like any yard sale, the equipment is as is. Okay, there are no guarantees. I would expect you to come out to the Alpha Ridge, look over the piece of equipment that you're interested in, and decide whether you want to put in a bid for it. The way that you'll be paying for it is online. We have that auction platform that we've used a couple times before. So all of the items will be on there, and you can go in and put in your bid for getting that item. And again, make sure you're on the list so that you can keep an eye out for when we announce the final details for this yard sale.
Jim, is it possible to reserve if we like something, if you publish the list, and if you're interested in any one of these items, would it be possible to reserve in advance?
Kind of like a buy it now option.
Yeah.
We're probably not going to do that because of the technical challenges with that. And plus the fact I really would like the person to
Come in.
and see it. You know, buying something from a yard sale without kicking the tires, without seeing it, I think is not a good idea. So
All right.
we're probably going to ask people to come out and look at what it is that they're buying before they
Understood.
buy it.
Thank you.
Okay, our talk this evening, Ernie, I apologize. I should have written up a big intro. And, you know,
That's
but
okay.
I think everybody knows just how great it is that you're in the club and you're a tremendous resource. So I'm going to turn it over to you as my voice is getting out and let you go ahead and provide your presentation.
All right.
So ladies and gentlemen, Ernie Wright.
Forward. Yeah, so I kind of want this to be informal. It's not a big formal talk, and I imagine almost everybody here knows these 4 amazing people are the first to go out of Earth orbit, the first to go to the moon since Apollo 17 in 1972. I was a member of the science team, and so our job was to prepare these people for science operations near the moon for observing as they flew by, and as they approached and left. And the nature of what we did involved, they had two Nikon D5 cameras. They had one Nikon Z9 camera. They had iPhones, which were a surprise to us. Normally, iPhones are verboten in an operational environment like that because they are not tested to be secure with all the other equipment that's going on. But I think they return a lot of personal imagery, so I'm not complaining about it.
Could you get a little closer to the mic or?
Well, yeah, that one.
Or I could
I'm not
just,
sure how well that one's working.
is it turned on? I don't think it is.
I was hearing it tap in the speakers earlier.
It's on the bottom of the side.
It is turned on. I think maybe the volume is really
Yeah, the
low.
door's locked, so I can't get in there right now.
Let's. This is at least for the folks that.
It's just online, so that's not gonna help us.
Yeah. So
At least we have to.
I'm gonna have to try to talk louder. Right, so they also had, they called them PCDs. These are portable computing devices. They're actually Microsoft Surface tablets from the year 2015 because we can't use anything new. It has to be space hardened and tested. Those tablets have been used on the ISS for years, so we knew they would work. And we also had vehicle cameras. These were the SAW cameras. The solar array wing cameras, basically GoPros, that were mounted on the ends of those solar arrays so that we would get continuous video feeds from those as well. And those photographs would not be through windows. So it's as close to being in space as you can get. The scientists came up with 10 priorities. I think 10 priorities is a lot. But these were the science themes that they went with. And so when they were designing the observation program, they wanted each of the observations they asked for to satisfy at least one of these science themes. And the stuff on the bottom is about what Artemis 2 was really all about. This is testing for future missions. The science program that we put together, that whole process had never been done before. So we were figuring out what would work in that and what wouldn't. And I'll get into a little more detail about that as well. I tell people that I was in mission control because that sounds cool, but mission control is an entire building at JSC. It's building 30. What people think of is that big room with all the monitors and the flight controllers. That's the flight control room. There are actually 3 of them in that building. Artemis 2 was run out of the white Ficker. The red Ficker was running ISS operations simultaneously, which is why you need more than one. And there is a third one in case it ever happens that there are 3 different independent missions going on. I was in the science evaluation room, or the SIR, that was on the 3rd floor of building 30. That's where most of the scientists were. But there was also the science mission operations room. This was where we received all of the data that was coming down from the spacecraft. Those were the first people to see all the photographs that you all saw from that mission. And this is the main thing that I was supposed to do. So I was the visualization lead on the science team, and I was supposed to visualize what the lunar flyby would look like. This is the actual trajectory of the flyby that they really flew, but I was making these for months using different illumination conditions and different timing for the flyby. This allowed the astronauts to train and the scientists to simulate missions. But this is what they actually saw. So we started the flyby operations a little earlier than we had planned because not much of the far side was illuminated on this flight day. But that gave them a really good look at the Oriental Basin, which is pretty tough to see from the near side. They got beautiful shots of Earthset and the Terminator.
And then they kind of waited for Earthrise, which is coming up in a second in this video. And then they turned the spacecraft away from the moon for almost an hour. The observation plan was almost 8 hours long. Mission operations was a little worried that that was too long for the batteries to hold out, so they had to turn the spacecraft and recharge the batteries and turn it back again for the eclipse that they experienced.
Is this simulation or real?
That is simulation. That's visualization. Yeah, that's what I rendered. So I actually rendered that on day 2 of the mission, and I'll talk about that a little bit later. But the idea is to make it photorealistic. This is not a novel idea. This idea of visualizing the mission beforehand. This is Apollo 8 as it's leaving orbit from the Earth, and that's 1968 in December. Those images were drawn on a UNIVAC 1170 by a Fortran 5 program. It drew that onto a CRT screen, which was photographed by a microfilm camera, and then the photographed images were printed on the pages of a training manual. So they never saw it animated like this. But we have been visualizing moon missions from the beginning. So crew training. This is like a couple of years ago, we started to have classrooms with the astronauts. And this was just basic moon and geology training. Sitting at the table facing us from left to right, Victor's all the way down there at the end. Jenny, Reed, Christina is hidden, Andre and Jeremy. Jenny and Andre were the alternates on this mission. They were also members of the closeout crew, so they were in the white room at the top of the gantry, buckling the seatbelts on the astronauts. They were wearing bunny suits, and I know that Andre was man number 2. They all had big numbers on their shoulder. Andre has also been selected for the Artemis 3 crew. And Jenny, meanwhile, was one of the Capcoms during Artemis 2. The Capcom is the capsule communicator, normally the only person allowed to talk to the astronauts during the mission. And for those early classrooms, I was making sort of visual aids to explain various things about the moon. This was, why do we have libration and longitude? And it's because the moon's orbit is elliptical, which means that sometimes it's going slower than a circular orbit would make it go, and sometimes it's going faster. So when it slows down, we see one side. When it speeds up, we see the other side. So that was the kind of thing they were teaching the astronauts initially. The other kind of training they did was in Iceland. A lot of the Icelandic terrain is kind of similar to the moon. It's basalt, it's volcanic. The person in the blue is Cindy Evans. She was one of the people on the science team as well. And that's Christina Cook in the red. You can tell Christina's really enjoying this. She spent 2 years in Antarctica, so she's kind of an adventurer anyway. On the left is a mission simulation. So as we got closer to the mission, we started to do these things where we would run down the timeline of an actual mission, and in real time, we would do all of the things that we would do during the mission. So Victor is sitting in front of a computer screen, pretending to look out the window at the moon. That's one of the movies that I made for that. Behind him, Christina is pointing the D5 at a poster of the moon that I made and practicing finding images in that. I mean, it had a 400 millimeter lens on it, so it was a lot like aiming a telescope, but you don't have a tripod. They found that even more interesting and something to learn in weightlessness. If you can imagine aiming a 400 millimeter telescope while you're floating around upside down. On the right is another classroom exercise, but this time they have the animations that I made, and they're practicing with those again. That is one of the D5s that Jeremy's holding on to. We were very careful to sit them at the correct distance from the image in order to simulate the field of view that they would have out the window. But Christina decided to do an unscheduled EVA. She got up and walked right up to the screen. Her task in that moment was to describe what she saw, and she just felt like she wanted to get up and see as much detail as she could. But the astronauts told her she was cheating. And I even had an opportunity to teach, I guess. I was telling them about lighting on the moon, illumination, and also trying to convince them that human eyes are better than robotic sensors. I don't have time today to go into the whole spiel that I gave them, but basically, there's a lot of complicated math that you have to do in order to normalize all the images that the robots take and form them into a mosaic. Whereas if you're an astronaut, you can look left and look right, and you have, the complete gestalt of the surface, and you can compare colors on this side and that side. You can watch the lighting change. They can do a lot of things that the robotic instruments can't do. One of the wackiest things that we did for training was inflate an 8-foot balloon of the moon and suspend that from a crane. The really shiny sort of spacecraft there is the simulator for Orion, one of the simulators. That's not the astronauts; those are cardboard cutouts.
Look like us.
Right? Those were all over the place, actually. And of course, I took a selfie with them too. They were in the lobby of Building 30. Yeah, I mean, if you point them the right, if you hadn't seen the feet, you're like, oh yeah, they're hanging out. I mean, they are somewhere in the building, but that's a picture that was taken when they were setting up the balloon, and this is imagery from inside the simulator as they practice aiming the camera through the window at the moon balloon. It was worth trying, but that moon balloon can't simulate different illumination conditions. It's static, and they're also looking at an angle that showed them a lot of the South Pole, which was not something that they could see on their actual flyby. So the geometry was a little weird, but it was interesting. So I was here February 12th, right? When I spoke for a few minutes about this mission. And at that point, we were not sure when we were going to go. That was right about the time that they had decided to roll the entire rocket off the launch pad back into the assembly building, take it apart, and fix the leaks that they had discovered. But it pretty soon became apparent that they were serious about launching on April 1st. And that's our reaction to that. We had worked for 2.5 years. This is 2 seconds after ignition. And I borrowed this slide from a colleague. She very helpfully put a yellow arrow where I'm sitting watching this business. We were all very excited, but it was also really stressful. We'd gotten to know these people, and they were sitting on top of 7 million pounds of thrust, and you just don't know what's going to happen. So you can see, there's a lot of happiness, a lot of tension, a lot of excitement, and just all the emotions. Before they set off for the moon, they did 2 orbits of the Earth. The first one was a low Earth orbit. They're testing really basic systems. The second one was this very high elliptical orbit that actually took 24 hours to complete. And during that time, they were testing communications and a lot of other things away from the safety of low Earth orbit, if you want. And then they did what's called the translunar injection burn, the TLI burn, that broke them out of that orbit and sent them to the moon. We designed the observation in 2 parts. That gap in the middle of the 2 red places is what I was talking about with turning the spacecraft around so that the solar panels face the sun. So they had 5 hours of lunar observation before they had to turn the spacecraft. They had another hour during the solar eclipse. Right after TLI is when this Hello World image was taken. You've probably heard by now that this is entirely lit by moonlight. And the reason they could do that is because the D5 allows you to set the ISO to 57,600. Yeah. Right. But what a fantastic image. I mean, you get a little bit of a zodiacal light there, and Venus is there. They actually took a series of images, and if you stack them all together, you can see satellites moving around the Earth. Polar orbiting satellites. And everybody's like, well, a pixel's way too big to see but you know, a star is even smaller in terms of the angle that it subtends. So that doesn't bother me. But what an amazing image.
Got the northern lights and southern lights, it looks like.
Yes, and the Earth is upside down, if it's not obvious. Southern lights are on top, northern lights on the bottom. Air glow, just everything you'd want from an image like that. And people were comparing this to the blue marble image that Jack Schmitt took on Apollo 17. And they were saying, look what climate change did to the Earth. I mean, climate change is a real thing, but this is lit by moonlight, and so it is going to look different. Yeah, that's Venus right there. Yeah. Yeah. So right after TLI, while they're taking that beautiful image and just kind of cruising in the spacecraft, that was my busiest day. I didn't know what lighting conditions to simulate until they had actually done the TLI burn, and I knew when they would arrive. There was always the possibility that something would go slightly wrong in that long elliptical orbit around the Earth, and they would have to wait an extra day, and that terminator would move another 12 degrees, and we'd see something completely different. So day 2, TLI burn, they give me the trajectory, and I have to render a movie that's 7.5 hours long that shows every potential target. And the reason for that is the scientists looked at that movie to decide what the astronauts should actually observe. You can trivially eliminate most of the targets on the night side, but then you have to decide, are there targets on the day side that aren't at very favorable angles? And this goes back to those science objectives that I was showing before, the science themes. Certain targets were in the list for certain kinds of observation. And even if it's in daylight, it might not be at a very favorable angle for the types of things that they wanted to see. So the scientists on day 3 had to make a list of all the things they wanted the astronauts to see and in what order, and then hand that off to a team called CLO. This is the Crew Lunar Observation Team, who created this software that runs on their PCDs and contains all of the targets in order for the astronauts. All they have to do is click on the next target, and it shows them a map, kind of a finder chart, how big it is, and it also shows what the previous target was and the next one was. So if you wanted to crater hop in that way, you could. The software would also tell you why the scientists want you to look at that. What is scientifically interesting about it? What questions do we want the astronauts to answer? Because we're hoping that the astronauts are the eyes of the science team. We want them to be proxy geologists. They get to actually go there and look. So we want to hear from them what they see. We want to hear if they observe color differences as their angle of view changes, all kinds of other things related to their science themes. And this is an image of them during the flyby, looking at the PCD in the upper left corner and photographing out the window. So they did this in pairs. 2 of them would be looking out the window, either observing or using the camera and two of them would be kind of sitting back, making sure, first of all, that the spacecraft is still healthy, but also sort of annotating what's going on. A sit rep is a situation report. That's a thing that the astronauts borrowed from the military. And it's just a thing where every 10, 15 minutes, they say, we're doing fine. We're switching teams. We're looking out the window, or we have lots of sun glare. We're going to put a t-shirt over the window that we didn't plan to cover. Sun glare actually proved to be a big problem. So this is all of us looking very busy. There was a webcam up in the ceiling in the corner on that left side, and they would cut to us periodically. And sometimes we'd get a warning, and all the tomfoolery that might have been going on stops for a minute. They show a picture of us being very busy, and then we move on. But there were also lots of moments during the flyby where we just stopped and either looked at the live stream from the GoPro cameras or heard something that the astronauts said that was just fantastic. And I was lucky enough that the photographer caught me in one of those moments. So these are the kinds of pictures that they were taking. This is a picture taken with the Z9, which had a 35 millimeter lens on it. This just looks like space to me. It looks like every space movie I've seen, where you're looking at the Earth over the limb of another body. You get this sort of sun lens flare stuff going on. It's just fantastic. And these are the kinds of images we got from the GoPro cameras. The nice thing about the way those were arranged is that they were pointed so that a little bit of the spacecraft was in the field of view. We knew what the exposure was. We kind of knew what the orientation was. And of course, I'm sure people have seen some of these magnificent 400 millimeter pictures of Earthset in this case, but also Earthrise. Years ago, I was here and gave a talk about the Apollo 8 Earthrise image and figuring out that Bill Anders was the one that had taken the picture. And for me to see this picture 55 years later, pretty cool. And the astronauts themselves were just amazed by the Terminator. In space, looking down there, Victor in particular said, if you fell into one of those, you would just keep on going. It didn't feel like it had a bottom. It just felt like it was a hole that went all the way through the moon. And so we're envious of their opportunity to see this in reality, because one of the other things they said was, it's just like the training, but in 3D. And to have the experience of seeing the moon in 3 dimensions, which even here, I mean, bino viewers, okay, but it's not like being there. They were just so excited about the Terminator. They went on and on about it. This is one of my favorite pictures. When it became clear that we were serious about the April 1st launch date, that was an opportunity to have a total solar eclipse. And for that date, it would last 53 minutes. But we had to kind of hustle a little bit. We had meetings with the flight surgeons and the astronauts to talk about eclipse safety, just like we did with everybody in 2024 and 2017. And I was one of the people that suggested they bring eclipse glasses. That was not something that was planned. So I ended up on an email chain with 28 other people figuring out whether or not it was okay to manifest 4 cardboard glasses. They asked me how much they weigh. They needed to figure out where they would be stowed. And it turned out when folded, they fit into, there's a pocket in the spacesuit where they put sort of a first aid kit, like Band-Aids and aspirins and stuff, and it would fit in that pocket. So they said, okay, that's where it'll go. The astronauts were thrilled. As you can see. And, I'm sure you've had the experience of putting those on and not being able to see anything. So how they all pointed in the same direction, I don't know. But this is what they saw. And nobody on the science team anticipated this view. I have heard comments from the astronauts that I can't repeat because they're not public yet. but some of the things they said, I mean, in real time, they were saying, this is science fiction. The human mind is not built for seeing this. We don't have words for this. We need to invent new adjectives. Because as soon as the sun disappeared behind the moon, they started to say, we see the entire moon. And we're all kind of scratching our heads because we weren't getting the live feed that looks like this. The exposure on the live feed was not showing us this. And we're like, what are they talking about? What do they mean they can see the whole moon? But it turns out that zodiacal light is a lot brighter than anybody anticipated, also called the F corona. Even though it's not the atmosphere of the sun, this is dust that is in orbit in the solar system. And you can kind of tell where the ecliptic is because there's an elongation from lower right to upper left. That bright spot in the upper left is Venus. The one down here is Saturn, I think. Saturn, Mars, Mercury were all visible on that right side.
Which one is that?
That's Venus. Venus, yeah, Venus is on the left. So I like this because it's in the Ficker during the flyby. The image on the left is one of the live feeds from the GoPro camera. The one on the right is my rendering of what they should be seeing. I love how much they matched up, but it's also an opportunity to point out all three of the science officers. Just like Mr. Spock, we had a science officer in the Ficker the whole time, and that was a completely new thing. Apollo never had a science officer in the flight control room. So on the left is Angela Garcia. She was on shift when Copy Moonjoy came out of the Capcom. She was the one that said that. The astronauts had gone on for like 20 minutes as they approached the moon, just with overwhelming enthusiasm and emotion. And then they kind of paused, waiting for NASA to respond. And Angela was like, I don't even know what to say. So she just said, copy Moonjoy. That's where that came from. In the middle is Kelsey Young. She was the head of the entire science team. And on the right is oh, come on, Mr. Graff. His first name will come to me in a second, but all three of them served as science officer in the Ficker throughout the mission. And I wanted to show you at least a few of the renders because I'm kind of proud of this, that I was able to anticipate what they were going to see and accurately tell the scientists what they were going to see. And they were able to use that to judge what they should observe. This is another one. They added Hertzsprung and Vavilov. Those actually weren't in the big list before, but they said, you know, we're going to get such a good view of those. And it turned out to be really useful as a size comparison with Oriental.
Could you explain?
Yeah.
Go ahead. Could you explain, please, what the circles represent on your diagrams there?
Yeah. So basically, we're just trying to say, where are these things? What are their boundaries? And that's a guide for the scientists, because depending on the illumination, you can't always tell where the rims of these craters are. I mean, if the sun is directly overhead, you can't see any shadows. You don't know how big they are. So the circles are always there, and that tells you kind of where they are. Around Oriental, that's a triple ring impact basin. And so there are 3 different circles around Oriental for the inner, middle, and outer rings of that basin. But yeah, just to identify where they are, kind of like dots on a map of cities. Except these are really big cities. I mean, both Hertzsprung and Oriental are several hundred kilometers wide.
And your rendering is the one on the right?
Yeah. Yeah, mine's always on the right. And I at least got this sort of second contact image of the sun setting behind the moon correct. But none of my renders anticipated that zodiacal light at all. On day 7, this was one of those things that the webcam captured. We were going to have an opportunity to debrief the astronauts. We were going to be able to talk directly to them, not through the Capcom. The science officer was going to talk to them directly for half an hour and ask them about their flyby experience. And that would be after they've had, time to rest and reflect a little bit about what they had seen. Also, ask them questions about things they said that the scientists didn't fully understand. Like, you said that Aristarchus Plateau was green. Do you mean like olive, or do you mean, what would you compare that to? And then immediately after that debrief, they had about a half hour set aside for opportunistic imaging. This just means we're not planning the targets. They can aim at whatever they want and take pictures. And I was asked what Apollo sites would be in their field of view. Now, they're not going to be able to see anything on the surface because it's far too small. But everybody wanted to know, what Apollo sites were they going to be able to photograph at this time? And it turns out 11, 12, and 14 were all in that field of view, even though we're not seeing a lot of daylight there. But that's what I'm doing, and everybody else is saying, no, it's a little higher than that. But people gave me a hard time about this image. It's like, oh, Professor Wright, look what you're doing. And that's what I'm pointing at, the one on the right. And the photograph they ended up taking is the one on the left. This is possibly, well, anyway, it's in my top 10. I was going to say it's my favorite photograph, but there are a lot of good ones. But this was one that I sort of glommed onto on day 8. We started to get pictures back from the astronauts. They started to download even before they had returned to Earth. All the lunar scientists were all over the craters and the lunar terrain, and that's their area of expertise, and it's what excites them. This image was kind of an orphan, this deep space image. And people were saying, oh, that must be a smudge on the lens in the lower right corner, or a fingerprint or something. I don't know if anybody has a guess, but I recognize that was the Large Magellanic Cloud. And once you figure that out and you're looking at the southern Milky Way, that big old pink thing is the Carina Nebula. The Southern Cross is over there in the lower left. There's a lot going on in there. And I was amazed that they were able to get this image. This is a 10-second exposure. Floating in space. And I learned later, I didn't know who had taken it, but I learned later that Jeremy had actually taken it. And he said that he could not see what he was aiming at. He didn't see that, he was aiming at this very rich part of the Milky Way, the southern Milky Way. He just kind of was winging it and pointed the camera out there, kind of hoping.
How do you stabilize it for 10 seconds?
I think he held it up against the window.
Okay, that's
right.
That was one of the things I was thinking of as a possibility.
Yeah, I mean, that's all I can figure. I didn't have an opportunity to debrief him about that. That's maybe coming in the future, because I have questions about this image that have not been answered yet. How the heck did he take it? But I think he braced the camera against the window. And I also think that he took this not out of any of the windows on the side. There is a window in the hatch at the top. That's apparently optically the best window. But that window was not pointed at the moon when they did the flyby. They just had an opportunity, a day or two later to use that window. And it's also a tight space. So I think it was easy for him to brace himself and brace the camera and just kind of say, let's let it go for 10 seconds.
Yeah, because there's a little bit of rotation at the edges, but it's,
right?
For 10 seconds, not like on a tripod, it's amazing.
Yeah, no, and I was thinking, I thought the image rotation was a clue too. And I actually think it may still be that the spacecraft is doing some kind of a barbecue roll. That's a That's a way to manage the temperature on the outside skin. And I think that's what we're seeing. But like I said, all kinds of questions about this image. Every day they choose kind of a one-page thing at the end of the report that they upload to the astronauts. It could be a cartoon from the newspaper. A couple of days it was sort of copies of the public reaction to their mission. And so this was just another page that was added to the PDF that had all the other things like make sure the toilet's still working and you're getting close to the Earth now, so turn around this way. On day 9, they sent my annotated image up there. That was pretty cool. Yeah.
Lifestyle question.
Okay.
When you're planning this mission and it's not like with the astronauts are up there in the space station for a long period of time and they can plan their sleep cycles, in a normal kind of path, but here you have to take advantage of the opportunities. How was that planned out when they actually got to rest? Were they even able to fall asleep?
Yeah, I mean it's hard in deep space to figure that out at all because the ISS is a luxury hotel by comparison. This is a minivan. And we were concerned in particular as a science team about the length of the observation plan. We had started out with a 3-hour plan and it somehow grew to 8 hours. The astronauts were like, yeah, we're willing to try it. And it turned out they were so excited and so enthusiastic about it that they didn't feel it until afterwards. And they came back and they said, that was kind of a long thing. But that's why it was a full day before we got to debrief them. They did have eating and sleeping and things happening in between. Even that hour or so when they had to turn the spacecraft around during the flyby, they were snacking and checking in on each other. We don't get to participate that much in mission operations other than how it affects the scientists. We were actually grateful that we were kind of invited to be part of mission operations at all. Science is a secondary thing when the risks are as high as they are on a test mission like this was. So we didn't get to tell them, yeah, they should sleep now, but the astronauts did. They were given exercise and sleep periods that they said, those are unrealistic. We're not going to be able to follow that. We're going to change that around. So they had some say about it.
Hi, Ernie, thank you. I was a little confused about the solar eclipse. What was eclipsing what? Was the Earth eclipsing the moon, or? The
moon was eclipsing the sun. So the sun is actually passing behind the moon as they fly around. It was just because of the shape of their trajectory and the fact that they were in the ecliptic plane. This is the plane that the Earth and the sun occupy. It would not have happened on any other April date and might not have happened for another 3 months of launch dates. So this was serendipity. Nobody planned for it. They didn't say, oh, we're going to launch on April 1st because there's a solar eclipse. It was like, we're going to launch on April 1st because that's when everything else is ready to go. It just happened that was an opportunity for observing something that really we had never seen before. We've never been that far away from an occulter in the middle of deep space, which is why we were so surprised by what they were able to see. And the astronauts too. I mean, we had no analog to prepare them for that. So obviously we were very excited that they made it down safely. One of the things a lot of people commented on, a lot of people who were maybe too young to remember Apollo, is the fact that it took about 2 hours to get them out of the capsule and into the raft and onto the boat and back to the ship. And that's normal. That was normal for Apollo. It takes a while to make sure that the capsule isn't outgassing with, hydrazine and all these other things that would instantly poison all the divers that were going in to get the astronauts. They needed to make sure it was safe for them to come out and make sure that everybody else could safely approach. And they have this very complicated, buoy system that they put all the way around the spacecraft so it doesn't suddenly tip upside down. But we were very excited to see them all.
Part of that was, and you never have from Apollo, the video technology has magnitude. The
Oh,
speed
yeah.
of descent
Oh, yeah.
is like nothing you've ever seen before in such high resolution. And detail when those parachutes, when second ones that was just free falling, you could see the capsule. You get the feel for the free fall that I never remember from Apollo.
Yeah.
That you
Oh,
felt
yeah.
that free fall from watching it on TV.
Oh, it was scary too, because yeah, I mean, some of the helicopter images were pointed straight down at the capsule. You couldn't tell how close it was to the water. It was like, are the parachutes going to come out? Are they going to hit the water? Yeah, well, and throughout the mission too, they had much better communications, much better video than Apollo ever did. The TV images from Apollo, they're like 120 lines at 10 frames a second in black and white, and they try to point them out the window and you couldn't see anything. This was like we were all there. It was like they were just posting on Instagram, which Reed actually did from space. And we could all share in it in a way that we couldn't with Apollo. Speaking of Apollo, it's very traditional to get out the cigars when the crew comes back safely. That's my friend Ben Feist. He created a website called Apollo in Real Time. And if you've never been to Apollo in real time, it's an experience. Ben has put together all of the audio from all of the tapes, synchronized it with photographs and video and film and transcripts and just all kinds of stuff. I had a very minor role in that, but yeah, I made a good friend out of that effort. And so he was handing out cigars and I was very happy to get one. I haven't smoked mine yet. I don't know if I will. It's a great keepsake, but that was something they did in the Ficker and the Apollo days, that all light up cigars. And I don't know how Poppy Northcutt felt about that. I don't think she smoked cigars, but everybody else in that room did. So we are continuing to look at all the data that we got back from this mission. We are going to publish a preliminary science report in October. It's going to be 150 pages of really cool science. One of the things I did was look at identifying which part of the lunar limb was cutting across that Earthrise image. You can kind of see mountains and valleys in there. So I was able to replicate the geometry of that situation. And based on that, I could identify what points were on the limb. And it's a little more complicated than you might expect, but a lot better than just drawing a straight line through it and saying, oh, close enough. That crater in the lower left, the big one, is Goddard, coincidentally, but all the Goddard folks were very excited about that. The one at the top is called Alberuni, and there's no emotional attachment to that one in particular, but the fact that the rim of Goddard crater was captured in that Earthrise image was very exciting for lots of people. I am happy to try to answer the question, what did it feel like to be on this mission? But I'm not sure I can enunciate it yet. I'm still processing it. It was like all the things all at once, but if I had to pick one thing that it was like that. I have never worked on a team that was so close-knit, so laser focused on the success of this mission. And so happy that it succeeded and everybody came back safe and we got lots of cool stuff out of it. So that concludes the talk, but I am happy to answer questions.
Any questions in the room?
You know when they plan to actually planning closely with deciding.
We're thinking about 2 years. But the thing to look for is how soon can Artemis 3 achieve its goals? So Artemis 3 is going to be an Earth orbiting mission. It is supposed to test docking with both of the lunar landers that we're building right now. So SpaceX has one giant Starship thing that they think they're going to get to the moon. Blue Origin has a more traditional lunar lander. Whoever wins Artemis 3 gets to be on Artemis 4. So the timing of the lunar landing mission depends on that, really crucially. And right now, we're a little worried about both of them. Starship has not orbited the Earth yet. It has launched and come back down, but it hasn't gone all the way around yet. And it has to go all the way to the moon. Blue Origin's New Glenn rocket blew up on the pad in spectacular fashion a few months ago. And it's going to take a little while to recover from that. So just like when I was here in February and I said, I don't know when we're going to launch Artemis 2. The honest answer is I don't know, but the plan is to launch it in 2 years.
What are you going to do with the next Artemis mission?
Well, the landed mission is actually going to land pretty near the South Pole, and they're going to be there for 10 days. They have experiments that they're going to bring with them. It's going to be a lot like Apollo, but it's going to be at the South Pole, which is really different from any of the landing sites near the equator where Apollo landed. So they're going to do similar things. But
Experiments.
I don't know.
Well, thank you.
Yeah, I mean, a lot of technology has vastly improved since Apollo. So a lot of the experiments will be much more detailed and much more informative.
Like maybe see if they can make fuel for going further to like Mars.
Testing the amount of water that's in the soil is one of the things they'd like to do. They're going to land an experiment that sees whether we can grow plants on the moon with regolith. Regolith is just the soil that's on the moon. You have to add stuff to it in order to make it fertile. We're going to bring a seismometer, which will measure moonquakes, much more sensitive than what Apollo left. And that's just the first landed mission. The long-term goal of Artemis is to build a base there so that we can stay there for long periods of time in the same way that we stay on the ISS for months now.
So how did the Apollo prove technology on Earth?
In 100 different ways. So all the miniaturization in your phone, that started with trying to get the computer on the lunar module small enough to fit and be light enough to serve that purpose. A lot of software innovations in that as well. That miniaturization really drove the industry. And that's kind of where, so the lunar module memory was core memory. And if you've ever seen core memory, it's a lot of little tiny wires with little washers in it. It's a billion times larger and heavier than anything you're familiar with now. But the fact that we needed to miniaturize that computer to put it on the lunar module and land it on the moon drove a lot of innovation. I didn't come prepared to have that whole discussion, but NASA has an entire website devoted to technological innovation. And it's the kind of thing that is easy to show once you start looking for it. But I mean, is that the reason we do these things? I don't think so. I think we go because we're going to go. I think we go because that's what people do.
I think one of the things that what I was told was like battery operated drills and stuff.
Yeah.
Came from all of that. So
yeah.
We're benefiting from all.
Oh yeah. And I mean, just the idea that you could have battery operated stuff like that. If you didn't invent it, maybe nobody would if there wasn't a reason to do it. Yeah.
So from an astronaut safety standpoint, because they're going to be outdoors more than anything, and that much time. with no shielding from any kind of ship. So do you know, or have they modified spacesuits in some way to help with extra protection against radiation?
That is a component of the spacesuit design that's going on right now. That's another limiting factor on when the landed mission will arrive because the spacesuits aren't ready. There are also a lot of contingencies. So the thing you really worry about is solar storm, coronal mass ejection. While you're sitting there on the surface of the moon, what do you do? Something that was tested on Artemis 1 is a vest. They put it on a mannequin because there were no people in Artemis 1, but they put a vest on a mannequin, and that provided an enormous amount of protection from radiation. And I don't think it's very different from the lead vest you wear when you go to the dentist and get your teeth x-rayed. But it was very effective. And so the other thing is, you know, if you have 5 minutes, is there one side of the lander that's better to stand on than the other? Can you be in the shadow of that radiation? If you have 3 hours, but you're in the rover and you're a mile away from your base camp, can you make it back? All of that stuff's being discussed.
Back in my Sony days, put the high definition camera on, especially Katie and Eileen Collins and all those guys. But we used to get the cameras back immediately after the ship, and we send the chips in because we were always trying to prove the cases. So when the chips,
Right.
it's because all the dead pixels from the radiation, and when you saw what it did to the chips, you can only imagine what that's going to be.
Well, and I am always cringing a little bit when I hear the astronauts talk about, yeah, we just see cosmic rays all the time when we close our eyes. These are little flashes of light. Just, you know, they're falling asleep and they see that stuff all the time. A lot of it's not as dangerous as that sounds, but who wants that? Who wants that kind of exposure? It's part of the risk of being an astronaut, part of the risk they accept about going up there. But obviously, we want to work on keeping them as safe as we can, particularly if the idea is to leave them on the surface for extended periods of time. We need to build habitation that is safe, that protects them from radiation in particular. Yeah.
Can you please talk about the far side of the moon? How long the astronauts spent time behind the moon far side? And I have one more stupid question.
There are no stupid questions.
Why is that they could not communicate with Earth when they're on the far side?
So I'm going to answer that one first. Because they're communicating by radio and the moon is in the way. It is literally blocking the signal. There is an effort underway to design a system that's like GPS and also like a satellite system called TDRS, which operates in Earth orbit, that would allow us to relay those communications around the moon. But there's just no radio signal that can pass through the moon. And right now, there's no relay satellite that can operate from the far side. So Artemis 2 experienced LOS, loss of signal, just like Apollo did. And that lasted 45 minutes. That was one of the other things that we used my rendering for because we weren't getting any live feed from them. So for that 45 minutes, that's how we could tell what they could see, even though we couldn't hear from them and we couldn't see anything. The first question is, it depends on what you mean by on the far side, but the 8 hours or so that we designed the observations for, the spacecraft was far side, you know, behind that plane that divides the moon into near and far sides. But at either end of them, they were pretty far away. So it's not clear that counts. But yeah, about 8 hours. And they did not go into orbit. This is unlike Apollo 8, which actually went into orbit, did 10 orbits, and then came back. This was a safety thing, mostly. We weren't trying to beat the Russians, who we thought were going to land on the moon in 2 weeks. We just wanted to see if we could get there and get back.
So, follow-up question. You said they were not in orbit.
They were not in orbit.
Then how did they get around?
The moon's orbit pulled them around like a slingshot. So the gravity of the moon is actually bending their path. And so they approach the moon. How many slides do I have to go back in order to see?
So it's just a flyby, right?
Yeah, it's just a flyby, but it's the gravity of the moon that's pulling them around.
Oh, okay. So
Right.
I got it. Yeah, I saw
Yeah,
that.
yeah.
Yeah, I never knew that. I never knew that was a flyby and not an order.
Yeah, they did not go into orbit.
Although it will count as one part, right?
Yeah, I know. Well,
Right? I mean,
the scale of this is a little deceptive too. The moon is moving a lot during the 10 days that they're out there, so that loop isn't really a loop. It's more of a, I don't know what you would call it, but it doesn't look like an orbit. It looks like a flyby.
so they could never see the same thing again in their mission.
That's
So
right.
Once they pass, it's done.
Yep. That's why it was important to plan the observations. You couldn't like, oh, we'll just get it on the next orbit. It's like, nope. Yeah.
I have one request.
Okay.
Can I get a picture with you?
Sure. Yeah, I'll stick around.
Are you gonna be involved in Artemis 4? And whatever follows?
I am 15 months away from 65.
Oh. Okay,
So it is an open question.
okay.
This was like the coolest thing I can imagine doing. I don't know if I can hold out until they actually land.
Understood.
Right. And maybe I want to watch it. I mean, one of the things about being in mission control is that I missed the whole thing. Everybody was watching this on social media and the news, and NASA had a continuous 10-day feed of everything that was going on. I missed all of that. I have no idea what the mission actually was. It was just me and I was there, but it's kind of like I was in this room, right? I didn't see all the public reaction. We were told a lot of things about how enthusiastically the public had embraced this mission, but I didn't see it and really until I got out of the room and came home. Well, my wife was sending me texts too. The thing about the webcam in the corner, I don't think I said this. There was a pillar in the middle of the room, and it just so happened that the angle of the webcam hit the pillar, and I was directly behind it. And so my wife complained to me, and I had to move my chair 6 inches so she could see me. I was kind of, if you remember Monsters Inc., I was kind of Mike Wazowski there. I was like, the whole room is in there except for me behind the pillar. But I was there, but I was kind of stuck in the room. And it's also a little bit like going to your own wedding. I mean, you don't remember that in any kind of way, the same way that all your guests do. You don't remember half of it at all. It's just like, how did we get here? So I kind of am looking forward to the opportunity to see it from the outside, honestly.
What were some of the challenges in shooting photography through the capsule window? Do you have distortion or field of view issues and reflection? You talked about reflections, but
Yeah, I think the biggest challenge for them was sunlight just everywhere. So it's even worse than on Earth. There's no atmosphere to scatter it. It's always direct, but once it gets into your capsule, it's bouncing all over the place. So they had shrouds. They had 2 of them that would cover 2 of the windows, but there were 4 windows. So they had to use T-shirts and, paper clips or whatever to hang the T-shirts on the other 2 windows so that they got it really dark in there. They also complained a little bit about the blinky lights on the inside, because once they started to dark adapt, those became annoying. On day 3, I think, but on the way to the moon, we also had an entire program for testing the quality of the windows. Are they foggy? Are they, distorting things? Are they changing the colors, which was really important to us? and the windows passed with flying colors. They were good.
Literally flying colors.
That's right.
So why did that, with all the time and space and with the shuttles and everything else and all the pictures that were taken, why was this different than anything before when it came to that part of the mission?
You have to design Orion to be light enough to make the trip. So the engineering is different from the ISS. The cupola weighs tons, just tons. The window material is very similar, but you just never know. It was in a different shape, a different configuration. It was maybe built by a different manufacturer.
Different piece parts.
You just don't know until you get up there and find out. The other thing is you're flying a different spacecraft. One of the big problems that Apollo had was not just outgassing from the insulation around the windows, but also stuff coming from the RCS, the rockets that steered it, would float around and then stick to the windows. And that's not a thing that you have to worry about on the ISS necessarily, but with Orion, it's a small spacecraft with lots of little steering rockets, and you don't know what's going to happen. There was also an issue with the urine dump. That follows the spacecraft all the way home, basically. Until you do another burn and kind of leave it behind. You're not giving it enough delta V to leave. So if you poorly designed this and it's floating in front of the windows, then that's a problem too. So we had a whole program within the science team to test the windows for who knows what problem might come up.
So to land on the moon, they need a bigger rocket. They can't use the same type of rocket they used to orbit.
They need more. So the Orion capsule can't land. So they need to send something that can land. We have given contracts to SpaceX and Blue Origin to design landers. SpaceX has the idea that they want to land a spacecraft that is 50 meters high on the moon. So if you look at Starship tests, there's like this rocket pasted on top of another rocket. That top half of it is what they want to land on the moon. Because the ultimate goal for SpaceX is to land that thing on Mars. And so they have to bring a bigger spacecraft that can take off from a deeper gravity well. So they're testing it out on the moon.
But who built the rocket that for Artemis 2?
That was a NASA project and NASA contractors.
So for Artemis 3, they're going to use a different rocket. They might use Starship, or
they're going to use a combination. So they will continue to use the SLS, the Space Launch System that NASA developed to launch the people. And then SpaceX will separately launch their Starship. And then they will dock, and then they will fly together to the moon. Or Blue Origin, whoever wins. But that's the idea, that they're going to launch separately. This is unlike Apollo, which put everything in Saturn V. Such an elegant solution.
So are we looking at, for Artemis 4, are you looking at like a command module lander system like they did for Apollo, or you'll land the whole thing and take the whole thing off?
No, kind of a command module lander situation.
Somebody's going to be there orbiting while they're on the moon.
Potentially, but Orion can fly itself too.
Mm-hmm.
I'm a little fuzzy on what the plan is because I think they are too. Only a couple of years ago, we were going to dock with Gateway, and Gateway was going to be in this weird halo orbit, and then there would be a different spacecraft that would also dock at Gateway, and then that one would have the lander. That's
I'm sure it's all in flux and it's not like
it kind of is
perfectly ironed out by any means.
Yeah, I mean, it's going to depend on which lander we pick too.
It seems almost impossible. I'm not being pessimistic. Just it takes so long to get everything tested and make sure we're comfortable enough to do the launch. And then there's even a decision on which one's going to go, let alone testing with Blue Origins.
Oh yeah,
it's successful with Blue Origins and it's successful with anything.
Yeah.
So
Yeah.
it's like, and then you're going to be all done in 2 years. Makes
Yep.
me look like a pessimist, not an optimist.
I will call it ambivalence about the plan because I have trouble believing that's going to happen too. And it plays a role in my thinking about retirement. I mean, I don't know if I can hang around that long.
Yeah, I'm not sure how you land a 17-story building on the southern area of the moon that's notoriously not flat.
Yep.
Without it toppling over when they get there.
It's very not flat.
I would tell them, but they learn so much more when they figure it out.
They're using a lot of lunar reconnaissance orbiter imagery to try and find a flat space for them to land. But the problem is it might not be next to anything interesting. It might not be in a place where you want to put a base. It's not a small problem. And one of the Artemis 2 astronauts has already come out and said, why are you landing at the South Pole? It's too hard. So I think that's an ongoing discussion. All right. We got one more question. Yeah.
Why isn't that we've never seen it?
We haven't seen it from space. You can see it yourself. There are seasons in which you can either be outside, you know, a half hour after sunset or a half hour before sunrise. And it looks like this big sort of triangular, cloudy, misty thing. And once you recognize it, it's easy to tell what it is. You might see planets right through the center of it because it's along the ecliptic where all the planets are. So we've seen it from the ground. We just didn't anticipate what it would look like from that vantage point, backlit by the sun. It was just crazy bright, way brighter than we expected. I mean, we knew it was there, but we didn't know it would look like that. And we didn't know the astronauts would have the reaction that they did. Yep.
Again,
All right, so I'm like 100 slides away from the end. I'm sure you can find it. Thanks, everybody. I felt a little silly being behind the lectern, but I want to make sure the microphone, at least for people online.
I want to sit there. All right, Wayne. Sure. Got the microphone there for the
Okay.
folks at home.
Okay, so here's this month's What's Up in Space headlines. Item number one is the Hubble Space Telescope finds a black hole in Omega Centauri, the globular cluster in the sort of southern hemisphere. Of course, many of you may know that we already knew there was a black hole, but that's an intermediate massive black hole. Didn't get that right, but it's a big, many hundreds of solar masses black hole. And what they have found here is the first stellar mass black hole in the cluster. They used many calibration images over the Hubble's lifetime, as well as some targeted science programs. Hubble observes Omega Centauri all the time for photometry calibration and for astrometry, positional calibration, and helps them do things like learn what the distortions in their cameras are and things like that. So they take pictures of Omega Centauri all the time. And they had 351 observations over almost 21-year baseline in order to do astrometric measurements of the stars. And you can see the picture here is HST image of Omega Centauri with an inset showing the star. If you look carefully, it's circled right in the middle of the inset. That is the star that they finally decided was around a black hole. So they did supplement the Hubble observations with a couple of JWST observations at two epochs separated by about a year, which is good because you have now an independent confirmation of the measurements you're making. So they discovered a binary pair. They watched a star, but only one of the two stars objects were visible. So they watched a star that was moving. Okay. It didn't seem to be moving around anything, wasn't moving in a straight line like proper motion or motion around the cluster center, that kind of thing. And they determined an orbit based on their 12 best astrometric positions. And they determined that the star orbits its unseen companion with a period of 94 years. Now remember, they only had 21-year baseline, so they did not even see a full orbit. They did happen to catch it near periastron, so it was moving fastest. So they got as big an arc as they could in that 21 years. And so it has a period of 94 years and a semi-major axis of 31 astronomical units, because we know the distance to the cluster very well. And we obviously measure the angular size of the orbits. And that infers a black hole mass of 4.5 solar masses. So it's a normal single star kind of mass. Massive star, but a single star mass. And of course, this comes through Kepler's third law, which I put down there. And I will point out that if you'll notice, Kepler's third law gives you the sum of the masses, not the mass of the black hole. It gives you the mass of both of them. And so they had photometric and spectroscopy observations that let them determine that the star that they could see was about 0.8 solar masses. Okay, so that they know the total mass, subtract off the 0.8, the rest must be the black hole. Okay, so that's the first object, or first item. The next one is Hubble, again, finds the declining star formation in the Andromeda Galaxy. This is a conclusion based on observations obtained through two Hubble programs, the Panchromatic Hubble Andromeda Southern Treasury, or FAST program, and the Panchromatic Hubble Andromeda Treasury, or FAT, program. They were able then to use those data to determine color magnitude diagrams in 6,500 separate regions that were all about 1/10 of a kiloparsec squared. So they were about 300 parsecs on a side at Andromeda, and all of them were out in the disk. And the color magnitude diagrams were then used to measure the star formation history in each of the 6,500 regions. So they have these regions, you'll see in a minute, and they can determine from the color magnitude diagrams what the history of star formation is by looking at the color magnitude diagram and fitting isochrones and seeing where you have star clumps in your diagram. The major results are that they found that the mean star formation rate over the whole disk, including the parts they extrapolated to the parts they didn't have observations for, and that was only 0.67 solar masses per year over the past 100 million years. So that's still a lot of stars. And it was, if you looked at a shorter time, it was only 0.43 solar masses per year. So if you looked at more recent time, you have less star formation over the past 20 million years. The decline was interpreted by the authors as, quote, late stages of a multi-giga-year wind down from a previously more active state. So far in the past, giga years ago, Andromeda was making stars very, very heavily, and it's been declined. They think it's been declining ever since. And so the fast, they also stated that the fast star formation histories agree well with GALAX observations. I forget what GALAX stands for, Galaxy Exploration Mission, something like that, but it's an ultraviolet mission that would let them measure star formation. And so the HST data and the GALAX observations agree with one another, which is a good confirming thing. And that suggests that the color magnitude diagram derives star formation history accurately describes recent star formation. Okay, get to the point here. Okay, we're going to see a movie, if I can get it started. So here is the Hubble data. So this is picture of the Andromeda Galaxy obtained by Hubble. You can see all the little squares. Those are individual pointings of Hubble. So this is a huge mosaic. I've seen the printed version of it, and it's like 31 feet across. It's panel after panel after panel in their printed version. And so this is the area that they use to do their color magnitude diagrams. And this is actually a movie. And what we're going to see is they're going to fade into their star formation data from their color magnitude diagrams. And then they're going to be separate time frames. The time frames will be noted on the bottom. So, and it loops several times. See if that starts it. Yeah, here we go. So the X marks the center of the galaxy. Brighter colors are higher star formation rate. And you can see the time scales at the bottom. They're now, this is the most recent. So now we're at 200 to 500 million years ago, 100 to 200 million years ago, 50 to 100, 25 to 50, and 0 to 25. So you can see that there's a steady decline in the rate of star formation as detected by the color magnitude diagram analysis. Now, it takes a lot of modeling, but it seems to be holding up. Okay.
So when they extrapolate that, that's say that that's similar to what we have in our galaxy.
I don't believe they didn't make that comparison, and I don't know that it's possible because you can do color magnitude diagrams here because everything's at the same distance, right? If you're going to look in our galaxy, now you got to know the distance to every individual object that you're including in your color magnitude diagram, and you know, so it becomes much harder. You got who? So it becomes much harder. So I don't think they can actually do that. Oh, okay. Okay. And finally, we're going to go into the realm of science fiction. JWST had an observation, had a program that looked for Dyson spheres. Dyson spheres, for those of you who may not be familiar with them, probably not anybody, were first scientifically proposed by the physicist Freeman Dyson in 1960, although similar ideas had been presented in various science fiction works prior to that. And the idea is that an advanced civilization will need more and more energy in order to do their thing. And so they will develop and build infrastructure to capture as much of their star's light as possible, up to possibly including completely enclosing it in a solid sphere to catch all the energy. Now, of course, you can't do that. Second law of thermodynamics says it'll still get out. So what happens is that if you do surround your star almost completely or completely, those objects will absorb the energy and will eventually re-radiate energy out, but that energy will have a lower temperature than the star, and so the star will suddenly will look like it has a lot of infrared energy instead of visible light energy. And so they look for something called an infrared excess in the stars. And a project called Hephaestos searched 5 million Milky Way stars for the anticipated infrared excess. And they found 7 candidates. Okay, so if they were all Dyson spheres, that says advanced civilizations aren't very common. So JWST was used to investigate the 2 strongest the candidates with the MIRI instrument, the mid-infrared instrument, because it's looking for the infrared excess and it's looking what's doing it. And in the case of these 2 strongest candidates, both candidates were found to have distant background galaxies that had the infrared excess. So the infrared excess was not associated with the star, but the data they had in their 5 million Milky Way stars survey wasn't high enough resolution to have seen this distant background galaxy. JWST could see the distant galaxy, so both of them were ruled out as Dyson spheres. The negative results, are still valuable because they are expected to improve future searches for Dyson spheres, because they now know they got to worry about those background galaxies, and so they will presumably be able to find ways to do it. And I think that's all of my slides, but I did want to bring up two informal things. First of all, I've reported a couple of times on the mission to save the Swift satellite. And for those of you who don't remember it, they launched a satellite to go up to connect to Swift, which is a gamma ray instrument or satellite. And they're going to boost it up to a higher orbit. Otherwise, sometime this fall, Swift is going to burn up in the atmosphere. It's our only gamma ray satellite that can tell us when gamma ray bursts happen. So they want to try to rescue it. So they did a crash program. The satellite they launched to do it, they launched successfully. During commissioning, they lost control of their satellite. It started tumbling because some of their attitude control system died on them. So they have recovered the satellite and they got control over it again. They've just uploaded a software update to revise their attitude control system, and they're working now toward going to rescue Swift. So it's still on, but they did have a major problem, but they got through it, I think. The other thing is, I want to remind you, the Roman Space Telescope launch is August 30th. I think it's like 7:25 in the morning Eastern time. So, okay.
Very good, thank you. All right, so we'll do a little bit of shallow skies here. Right now, Venus is in the evening sky in the west. It is actually last night, 12th. It is at what they call dichotomy, which is an exact half phase. However, if you can manage to see Venus over the next night or two, you may see that it doesn't, to your eye, quite look exactly half. And that's called the Schroeder effect. And basically, it is the way that the sunlight hits the clouds. When we have eastern elongations, it's a little bit chubby. So it kind of looks like you're supposed to be at the half phase and you're not quite there. When it's in the morning sky, it's the opposite. It's a little bit shy and it takes a few more days before it looks like it is exactly half phase. So that's kind of an interesting visual piece of astronomy you could do on Venus. Mars right now is in Gemini. It's still really small for you visually, but if you are taking images through your telescope, it's fairly decent. You can still do stuff at 5 arc seconds, and it is getting higher and higher in the morning twilight. Saturn is rising late in the evening, like around 10 o'clock. So it's getting more reasonable to try to take a look at Saturn. It will be heading for an October opposition. So one of the interesting things right now with Saturn is something called spokes. I don't know if you can see on the video here, this little like dark area. Basically, spokes are these ice dust in the Saturn's rings that get lifted slightly above the ring plane. And then depending on the lighting, they will either appear as dark patches or light patches. So it's an interaction between the solar wind and Saturn's magnetic field that causes these. They are seasonal in that they are usually seen near the equinox. And of course, last year in May was the equinox. So we're just kind of coming out of the equinox. So right now is a prime time for catching these spokes. I think James Willingham actually posted in the Howard Astro list an image he took the other night where he believes he caught one of those spokes. They actually, there's an interesting history behind them in that Steve O'Mara, who is one of the most skilled visual observers, actually saw those. And it took until Voyager went by to confirm that what he actually saw with his eye was for real. So at any rate, right now we're in spoke season, which is kind of interesting if you're imaging Saturn. And it will continue to weaken now that we're past equinox. Let's see if I can hide this here. Okay, the big thing is that we have an eclipse. It is almost total at the end of the month. It's very deep, 96.2%. At the bottom here, you can see there was one, I think that was like 98% a few years ago. Usually, even though it's not total, it's still a very cool presentation because you're going to have the bottom part kind of reddish glow and then the top kind of white, almost like a Mars scenario. So it starts at 10:34 for us, peaks at a little after midnight, 12:13, and then ends at 1:52. So this is really ideal if we can just get some clear skies, because it's going to be very high, should be very visible. The Americas, Europe, Africa, Eastern Pacific, but we are really in the sweet spot for this one. So like I said, the northern tip of the moon is going to remain in sunlight, and the southern part will be kind of in an orangish color. So it's going to maybe remind you of Mars with a polar ice cap. And with most eclipses, naked eye binoculars, great to use. You don't need a telescope. However, if you do have a telescope and you are interested, you could do crater timings. So you basically observe when certain craters, when the shadow is midpoint through the crater, you note the time. And why would you want to do such a thing? Well, basically, that data can help scientists measure changes in the Earth's shadow, the size, from eclipse to eclipse, because we have a fair amount of historical data like this. And so we can add to that existing database. You can do this. It doesn't take a lot of training, doesn't take a huge amount of skill. You need a telescope with magnification of about 50 to 90 and a good moon map. And you also have to have a good way to get your time exact, which your cell phone would be perfect for. So as I said, you record the moment that the shadow crosses the center of each crater using an accurate UTC time. And you can get a list of these crater timings at the Alpo. The front page of the Alpo has, and on its eclipse page, has a blog entry about it. And you can download the sheet with the predicted timings. That can be your worksheet if you are going to participate. And so I would encourage you, if you want to do a little bit of science, you can do these crater timings if we get some clear skies for this partial eclipse. To our astrophotos. Sundar, you did an amazing job. Last month, we talked about using your Pixel or your Android phone. You want to tell us briefly about this one?
Yes, I mean, it's just automatic. I use this phone, Google Pixel phone, and we have an Astro mode in this. And I put it in the time lapse. It takes a time lapse of 4 minutes. And it compresses that to just 1 second time lapse. And I took this at the Cherry Springs State Park, which is a dark sky, official dark sky park in Pennsylvania. I drove 5 hours for this, but I was lucky. It was not clouded out.
Yeah.
No rain. And I actually checked the astrophytes for this, and it was supposed to be a good day. And I was lucky. I went there 2 days. Both the days, the cloud just cleared out just before the Milky Way showed up. It's around 10 o'clock.
Yeah.
10, the Milky Way showed up. I enhanced it a little bit, just a little bit, using the AI feature in the camp and the phone. But it was amazing. I have taken a lot of photos like this in different from different parts of Maryland and Pennsylvania. But this one is the best from the East Coast. The one that is better than this was taken at Mauna Kea in Hawaii.
Oh, okay.
I went to Mauna Kea, and I had no clue how to take these things.
Yeah.
So I took it with my son's iPhone 13 phone. I was not into stargazing at that time, So the picture, even though it was not taken with a good care, with phone or something, it came out nice, but for naked eye observation, that was the best one.
Yeah.
Because it's about 1 or something.
Well, it's just very cool. I mean, we talked about this last month, and to see you actually pulled it off and did a great picture, with your cell phone. That's awesome.
And thank you, Jim, for your helpful hints.
Oh,
You've given me a lot of
you're welcome. And then here are 2 more from Cherry Springs,
Yeah.
and
I
these are
can't
your
take
Sea
credit.
Star.
I can't take credit. It's the lunar scope takes credit for this. All I have to do is just point it and set it and then go. And
But it just shows you again what the Sea Star can do.
And Sea Star does a very good job of doing this if you happen to be in a dark sky area. And this, I could not even believe my eyes. It was so nice. I couldn't see a thing with my naked eye, all from the telescope.
Mhm.
I had a telescope with me, but Sea Star was able to see all these things. That's nice.
Great.
And again, thanks to the club.
Absolutely. All right, on to the object of the month. So this is the Trifid, I think, or is this the Tulip? The Tulip Nebula.
No, it's Trifid.
Is it Trifid?
Yeah.
Trifid, okay. I need to put my glasses on. Trifid Nebula. And Gene Handler pulled this one off. Gorgeous, absolutely gorgeous. Gene, are you on? You want to say anything? All right, the other object of the month winner was Jose, and his, I think you call this the Hubble palette, right? For M16. Just again, a gorgeous photo of this.
I actually combine my the Hubble palette with some RGB data I had for the stars. Instead of just using it for the stars, I used it for everything else, and I got this nice colors. So it was interesting to experiment with it.
Yeah, very, very cool, very aesthetic. Our own Wayne Baggett here
That's
is,
my attempt at it.
yeah, very nice.
I
With-
also used the HLO, the H alpha and oxygen 3 with RGB stars.
Was this taken at one of the star parties, the
This was
impromptus?
July 13th, Star Party Values.
Very nice souvenir from that party.
It's amazing you could take this much clearer images from average.
Yeah.
Which is bottom 5, right?
Yep, so this is the North American Nebula that I took with my Sea Star, the S30 Pro. I took it over a couple different nights out at Deep Creek Lake, which is a little darker than it is at home. And then it's my first time just playing around with the narrowband normalization and PixInsight to kind of try to get it a little more interesting than just red. So pretty happy with how it came out.
That's very nice.
Was it Sea Star?
Yeah, the S30
S30.
Pro.
Small.
Yeah, the Pro version. This is an experiment that I did with with my brother-in-law who also has an S30 Pro. So out at Thermont, we aimed both of our telescopes at the Crescent Nebula, and we had 4 or 5 straight nights of clear skies. And so between the 2 of us, we had almost 40 hours. And then once you pulled out all of the bad subs and stuff, I still well over 20 hours, 25-ish hours on this.
Wow.
Combining the 2 of the data together. And so this was what I ended up with on my process.
That's amazing.
I'm just shooting my way through the Messier catalog, so using the S30 Pro with some 2x dithering works out pretty well for these star clusters.
How long was it?
How long was that one?
Exposure?
The exposure on M5?
It's in the data. I forget because this one I was actually late in processing, so I took that like over a month ago. But
Maybe hours.
yeah,
51
not
minutes.
even quite an hour.
Yeah.
Okay.
Using it in equatorial mode or out there?
Yeah, I have it set on a tripod with an equatorial mount.
I was wondering why you were doing that. But it's equatorial, I understand.
Yeah.
And yesterday's eclipse, that's my little effort from the backyard, and fortunately cleared up enough.
Yeah.
And saw that on Facebook. I thought that was pretty good.
I don't know if anybody else saw this, but we were starting to see news reports that said you could look through a colander.
Oh,
in the eclipse. Oh, no. So strain my eyes.
Darwin effects.
I wonder if optometrist appointments spike.
Okay, we've got a wonderful montage here from Michael. He also had a little time lapse, which was cool, but unfortunately the animated GIF would not play, and I didn't have time to work out that all the issues to troubleshoot that. But this is really great. This reminds me, Herman Hein used to do this sort of thing, and he used to do it on film, and like with multiple exposures, take one, position it. How in the world he did that back in the 70s and 80s, I'll never know. Of course, today with something like C-Star and digital technology, it's much easier, but still, nonetheless, again, really kind of cool what you can do. C-Stars are great for recording eclipses, just great instruments. And Wes has one more here. His, I was able to load, it came as a video. So here is yesterday's teeny tiny partial eclipse. I was texting with one of my friends. He's like, oh, I bet the birds are going to go nuts. I'm like, no, I don't think so.
They did in the UK.
I want to know what features are on the web. If only we knew somebody.
Only if we knew somebody who could
Take a note here.
Very nice.
Yes, ZWO has some sort of software issue with their time lapse function. Because in the video it spat out, jumped around a bit, and there were parts where it was jumping around, and there were enough clouds that I could see that the clouds were illuminated through the solar filter to the edge, and then the sun would make these one frame jumps. And in that one frame, I could see a hard line where the clouds ended at the frame edge, except they were, this far from the frame edge. So I have no idea what it's doing, but I ran it through PIPP to stabilize, and it did a pretty good job, other than at the beginning where it's in the clouds and it couldn't quite define the disk.
Yeah.
Solar Dynamics Observatory has the same problem. It's designed to aim at the sun, and anytime it experiences a partial eclipse, it just starts doing this.
Yeah, but it doesn't even have anything to do with the eclipse. If I go out, not now, but if I go out tomorrow with the sun with no eclipse and do a time lapse with the C-Star, the sun jumps around. Because I saw people in the Facebook groups complaining that the sun was doing that, and people were like, well, turn off keep it centered and turn, and just readjust the tracking every now and then. It's clearly software, because when it makes those little super fast jumps, you can see the hard edge of the frame, but 200 pixels away from the actual edge.
Huh.
So it's something in the software is making it do that. I have no idea.
You gotta use a colander filter.
You have forgot something.
Dollar star.
All right, folks, and that's going to bring us to the end. We do have a planning meeting September the 7th. Again, you're always welcome to join us. The link is on the HAL website. Join us with any ideas about things you'd like to see us doing. And our next meeting is September the 10th. So everyone be safe driving home, and thank you again for coming out. Ernie, thank you so much.
Great meeting.
Thank you.
Really.
I'm happy